Now let's look at some forecasting methods and start working on some data to actually build the forecasts. So this is what the forecasting problem essentially looks like. You have some variable of interest, we're going to call it y, and it has different values it takes over time. So we're going to indicate the time index by the subscript t. Okay. So let's look at this picture at the bottom of the screen. Yt indicates the value at time t. And in this example, this is the current value. So if you're sitting in October, this would be y of 10 if we have monthly data for the value of y for October. Then the previous value will have a subscript which is 1 less. So if this is y of 10, the previous value in time would be y of 9, the value of y for September. And the previous value will be y of 10 minus 2 or y of 8 and so on. So you have these values over time, whereas when you go forward in time, the subscript t increases. So that's just a label to represent those values. And we can see from this picture that the dotted line separates the future from the present and the past. And so right now we have observations up to YT, let's say all the data up to October. And now we have to forecast the demand for November, December, and January. So November will be YT plus 1 or Y of 11, December will be YT plus 2 or Y of 12, and then January the next year will be Y of T plus 3 or Y of 13. So that's the general problem where you have a series of values over time, and they stop at a certain point in time, like YT here, and then you have to forecast what's going to happen after that time with this series of values. The variable Y could represent demand, or which is our demand for a product. It could represent the gross domestic product GDP of a country. It could represent a price. It could represent some transportation volume or quantity. Depending on our problem, whatever we need to forecast, it would represent that value. And this sort of data where values are of the same variable are given to us for multiple periods of time is called time series data. So forecasting naturally deals with time series data. In time series data, often there's some correlation of the values over time. So if you look at the values which are 1 month apart, like YT and YT minus 1, there's going to be some correlation, because even though things change, there's some carry forward effect. So if a company is doing well in October, it's likely to be doing well in November, right? And so the values over time are related, but they're not exactly the same. Each month brings its unique things. And it doesn't have to be monthly data. It could be daily data, could be hourly data, could be weekly data, could be data per minute, right? If YT refers to a minute, then T minus 1 is the minute before. So depending on what you're forecasting, the data could have different time scale. Now, when we want to forecast YT plus 1, which is shown right here, okay, this is a very important slide because it gives you a conceptual view of what's happening. And here what I'm trying to show is what are all the things that could be influencing y of t plus 1. Okay, so obviously the past values of y are going to be correlated with y of t plus 1. There's going to be some influence. That's this big blue arrow. So that's what time series methods try to do. They look at the past values to try to extract some pattern, and there's always going to be noise. By noise, I mean unique things that happen in each month. So every time period, every month, every week has some unique events happening which could affect our demand, and then they might not be repeated, at least in the near future. And there's some unique elements. Those are the clouds. They're unobserved things that are influencing our Y values, and I've drawn clouds because I don't know what they are, but there are some unobserved things affecting my Y values. We can call them noise, we can call them error, we can call them unexplained part of Y. So at each time period, some noise or some unexplained variation is affecting my Y values. But Y values are also affected by the past values because they're correlated. The past has some carry forward effect. and that is this blue arrow. So the time series forecasting methods are focusing on this blue arrow, linking these past values to the future value. So time series forecasting methods are going to look at the past values of the same variable and try to identify patterns that they can project forward and try to predict the future value. Now, time series is not the only way to forecast. We may also have something like Z. Z is an observed and leading predictor of Y. What do I mean by leading predictor? It means that values of Z for a particular time tell me something about my demand Y in the future. So for example, these could be reservations at a hotel. So if YT are my weekly sales in a hotel through room bookings or my weekly room bookings, then ZT could be the reservations that are available that have been made for those rooms the prior week. So imagine for next week, we have some reservations already. Some people just book rooms early, right? If we have more reservations for next week than we usually do, then that's a sign that next week's demand is going to be high. So reservations in hoteling industry are what we call a leading indicator because they happen at an earlier time, but they tell us something about the future. Another example of a leading predictor or indicator can be in construction. So construction permits are often given in advance of construction actually happening. So if I am a company that sells products used in constructions like PVC pipes or wood planks, if I see that a lot of construction permits are being given out in May, then I can guess that in June a lot of new construction will start and they'll need to buy wood and so forth and concrete and so on, right? So the issuance of construction permits can be a leading predictor of sales of construction materials. Okay, because the permits given out in May not be a good predictor of construction related sales in May, because if a permit is given out in May, it may be a while, like a couple of weeks or so, before the construction actually starts. So a lot of the permits given out in may have construction beginning in June and July and so on. So the permits may have an effect on the future months, but not on the current months. Okay. So if we do find leading predictors, we can use them like this, where to predict the value YT plus 1, we have a time series model, but we add to the model the variable Z, and we combine the variable Z with the time series information to try to have a better prediction of YT plus 1. And notice to predict YT plus 1, we already know ZT because everything before this vertical dotted line is already observed. It's in the present or past. Okay, so there are known values up to the dotted line. And because Z is a leading or early predictor of Y, this gets observed first before YT plus 1 is observed, so it can be used to forecast YT plus 1. What if we have a variable X which predicts Y, but it is not a leading predictor? It predicts Y in the same time period. So imagine that X is, we are sitting in a large city. Maybe we're a business in the downtown of that city where there's like a big convention center where lots of music concerts happen. And so XT is how many music concerts are going to happen in a particular month. Okay, the music concerts that happen in that particular month may influence the sales of T-shirts or merchandise like associated with those bands. So like custom merchandise, goodies to do with that band or event. So whatever events are happening in the convention center, they influence the sales of the businesses around, which is like T-shirts or other things like that, right? But a convention happening, an event or a concert happening in June is not going to influence the sales in July because newer things will be happening in July that will be influencing the sales in July. So it's kind of concurrent, right? So if we can figure out how many events happen in a month, they could affect the sales of food stalls around there or other things around that. Other examples could be anything that's associated to your industry. So for example, you could be XT could be the employment or new jobs that are posted in a particular month or made available in a particular month, or given out, or new jobs that are filled in a particular month. So that's like an economic indicator. And YT could be sales of appliances or furniture. And we know that when economy does well, big ticket items like appliances and furniture, the sales tend to go up. When the economy is not doing well, people are not getting jobs, then the sales of big ticket items tend to fall. People tend to keep using their old appliances and furniture and so on, right? So if this is the jobs report for a particular month, that jobs report may influence the sales in that month of appliances. But the jobs report for June, let's say this is quarterly data, so quarter one jobs report may not affect the sales in quarter two, because quarter two has its own jobs report, and economy can change sufficiently from quarter to quarter that quarter two's economic conditions are going to impact the sales in quarter two. So a lot of economic indicators could be something like X. In those cases, for economic indicators, often economists put out forecasts. So we may know the economic indicators for quarter one that are influencing the sales in quarter one, but economists may have predicted the GDP for quarter two or the jobs they expect to see in quarter two. And then to build the forecast for the next quarter, we could use the forecast that was built by economists or other people who are professionals for that part of the economy or that economic indicator, and we say, oh, this is a very reliable forecast, so I can use XT plus, even though XT plus 1 is not observed, I don't know the jobs report for next quarter, I don't know the GDP growth for next quarter, I have a good forecast for it sitting in quarter one. I already know the quarter two forecast, so I can plug in the quarter two forecast in my prediction for YT plus 1 and try to use that. If nobody is building that forecast for the next quarter, you can just use the previous quarter's value like XT, because XT is going to have some correlation with XT plus 1. They're correlated. So if XT plus 1 is unknown, I can just draw an arrow from XT to YT plus 1 and try to use XT. We call this a lagged variable. So I'm using a previous value of a variable to forecast a period in time which is ahead of that old value. So I can, just like ZT, the arrow goes to the future value, I can treat XT as a leading predictor and draw an arrow from XT to YT plus 1 and try to use XT like a leading predictor, because I know the values of X over time are correlated. So even though I don't know XT plus 1, conceptually XT plus 1 makes more sense conceptually, but because I don't have XT plus 1, I can just use XT because it's going to be correlated with XT plus 1 to get some boost to my forecasting. So I can treat XT as a leading predictor like Z of T, or if the forecast of XT plus 1 is available, I can use the forecast of XT plus 1 to get YT plus 1. So in other words, when we build our forecasting methods, you'll see these sorts of ideas reused again and again. Some forecasting methods will try to rely on the time series aspect, look at old values of the same variable we are trying to forecast, the same time series. Other methods will try to bring in leading indicators. Other methods will have these lagged variables where conceptually the future value makes sense, but we don't have it, so we use a lagged value, or we use a forecast of that variable. So using other variables that tell us about Y, as well as using the data, the time series correlations from time series data, is how we try to build the forecast for Y. Okay. So just keep this picture in mind that YT plus 1 is being affected by the patterns that stay consistent over time, so time series aspect, as well as other variables. And you may use the other variables in a leading predictor sense, where the old value of the other variable affects the future value, or you may use it as a current predictor, where you have a forecast of that variable and you use the forecasted value of that variable to predict your variable YT plus 1, as well as these other aspects of it. And then there's always going to be, unobserved things affecting your variable of interest, which you don't know about, which are referred to by clouds. There's also going to be some unexplained parts. So that's why your focus is never going to be 100% accurate. And so that's the noise in the data, or the unique aspects that happen in every time period that are not driven by old data or historical data. Okay, so Let's look at some classes of methods or categories of methods that people use. So we talked about time series method on the previous slide. They rely on past values of y only to predict yt plus 1. So time series methods are not going to have these x and z variables in the model. They're only going to have past values of y in the model, and they're going to try to predict the values of y plus 1. These are the methods we focus on mostly in this course. They're classical methods. They perform reasonably well. Because why? Why do they perform reasonably well? Well, look at it here. Okay. When I study yt minus 1, yt plus, minus 2, these old values of y contain within them the influence of the old values of x and z. So even though I don't use x and z explicitly, the old values of y have within them some influence of x and z. So if I only study the old values of y, I have not thrown away x and z. They are part of the old values of y because they've been affecting the old values. So bundled up in the old values of y are influences of a lot of different variables. And if I can detect patterns in y, the patterns will capture some of the influence of the past values of x and z as well. So the past values of y act like a proxy for all sorts of influences on y. And if I can detect patterns in the past values of y, that can give me good forecast for yt plus 1. So that's why historically a lot of people have used time series methods, and that's what we focus on in this course. Then we can focus just on the predictors and forget the time series. So forget yt minus 1. Only use the xt plus 1 forecast or xt and zt to build a forecast of yt plus 1. And that's called causal or regression methods, where you predict y, and you can have a time variable as well, which is index 1, 2, 3, 4 to capture a time trend, but you don't use the past values of y. So the yt plus 1 forecast is just based on variables x and z or variables like them, and a variable indicating the time 1, 2, 3, 4 like that, like indicating the time, and we don't use the past values of y, and that's called regression methods or causal methods. Okay. Then we can combine the two. So we can combine this whole picture into one method, have time series as well as x and z. And those are called a RIMA X or dynamic regression, where you have predictor variables like x and z, and you also have the past values of y. We don't study this in this course, but if you take advanced supply chain courses, you will study ARIMA methods, seasonal ARIMA methods, and then ARIMA X or seasonal ARIMA X methods to combine the whole picture. And then if you take an advanced data analytics course, you learn machine learning approaches for forecasting and recent forecasting competitions where they give the same time series to a bunch of teams and they try to come up with a forecast, and then they show them the future values and calculate the error and check which team had the lowest forecast error. So recent time series competitions have shown that machine learning methods like random forests, decision trees, and these sorts of approaches perform pretty well in forecasting, and they can even beat these ARIMA X and so on methods. So these you would have to take a course focused on analytics and machine learning to learn those. The first two we'll cover in this course. The third one I do cover in the advanced courses, and then we also have advanced business analytics courses that will cover the fourth one. So if you take a lot of courses with us, you'll probably get the whole deal, but at least with me you'll get the first three across a couple of courses, and in this course we'll look at the first two mostly. Sometimes these methods like ARIMA and seasonal ARIMA will not cover in this course, but in the advanced courses we do cover those. So what is a time series? It's a repeated observation. A time series is the repeated observations of the values of a variable of interest in their order of occurrence. Order is important. So the most recent value, then the value before that, the value before that, the value before that, they have to be in order. And when we analyze time series data, we want to pick the appropriate method to use because we have multiple time series forecasting methods. And which method we pick depends on what are the components the time series have. And we're going to look at these 5 components of a time series data, where we'll say that a time series may have a level component, which is basically the time series is just random variations around an average. So let's say consumption of bread is very stable. So the local grocery store sees on average the same consumption of bread or sales of bread. But obviously every day or every week there's a little bit different consumption. It goes up and down around the average. Let's say on average they sell 500 loaves of bread in a week. Then on any given week they may sell 520, then 480, then 545, then 490. So it may go up and down around 500, but there is a level of 500 that it tends to be around. So that's called a level component. So Y values hover around some mean value. And then a trend means there's an increase or decrease over time. Then seasonal means that after a certain time period, a pattern repeats. So if there's monthly seasonality, which is very common in many products, then you see a lot of sales for certain months, then less sales. When the same months come back the next year, you see the sales go up again. So like summer products, think about swimwear, sunscreen, the sales would go up in the summer months, then fall down, then next summer again go up, then fall down. So this pattern over 12 months will repeat. So for the first 12 months, whatever pattern you see in terms of increase and decrease, you'll see the same pattern relatively the next year, the same pattern. Not exactly the same, there'll be some variation, but approximately the same. And that's called seasonality. Winter jackets, sales go up in winter, go down in summer. A lot of products like consumer goods sell a lot around the holiday season, toys, chocolates, even clothes and shoes, because when they go on sale around Thanksgiving, Christmas. And so you see the seasonality, monthly seasonality for a lot of demand data. Then you could have quarterly seasonality, which is kind of like monthly seasonality, but if you're looking at quarterly data, you see it in quarterly seasonality as well. You may see day of the week seasonality. So on weekends, let's say you are a barber shop, you might see more people come in to get haircuts on the weekend. So Saturday, Sunday, your sales go up, then they fall and are less in the weekdays. So that's day of the week seasonality. You may see date of the month seasonality. Let's say people get their paycheck on the first or the last day of the month, and then the first of the next month they're feeling like they have money in the bank, so they go and do more shopping. So a retail store may see more sales on the first week of each month, and then the sales drop in week 2, week 3, week 4, and then whatever days are left, and then they again go up on the first few days of every month. You see higher sales than the last few days of the month. Then cyclical patterns are patterns which repeat over multiple years. So let's say there's a business cycle, and every 7 to 10 years we have a recession. So we see, the company level sales, they tend to increase for a few years. Then, a downturn happens, they go down. Recession happens, they go down even more. Then they bounce back, increase, and then they go down again. And this sort of business cycle over 5 to 10 years repeats every 10 years or so. Or maybe it doesn't repeat exactly 10 years, but sometimes it's 7 years, sometimes it's 10 years, sometimes it's 12 years. On average, around 10 years, it repeats a boom-bust type of cycle. And that would be like a cyclical pattern. Because you need many, many years of data to observe this pattern. So let's say you had a cyclical pattern that repeats every 7, 8, 9 years or whatever, you might need to have 30 years of data to get enough repetitions of the cycle to use it for your forecasting. And usually, very old data is not relevant. What happened 30 years ago may not be that relevant for what's going to happen tomorrow. And so often when we are forecasting for the short term, the next month, the next few months, the next year, we don't really care what happened 30, 20 years ago. And so we don't use like 30 years of data. We're often using just a few years of data. And with a few years of data, you don't see the cycle repeat multiple times to be able to capture it really well. And so this is mostly ignored in the type of forecasting we're going to be doing. If you want to do long-term forecasting, like forecasting the next 5 to 10 years, you would probably need to consider it. But because that's often not done for sometimes for capacity decisions, you want to look at what capacity you'll need 5 years down the line. But often you use a lot of judgment forecasting methods where you bring your judgment to play and not like time series method. You don't really use time series method to forecast 5 years out. And so we're going to ignore this. We just need to know conceptually what this is, but we're not going to put this into our models, our time series models. And then there's some going to be unexplained part of why that appears random to us. Something is causing it, or maybe it's just random, but we don't know, and we have no idea what's causing it. We can't predict that. So let's see what do these look like. So if you have data that looks something like this over time, you can plot over time. right? This could be sales quantity over time. This we'll say has a level or a horizontal component because, on average, we're at the same level of quantity and we have some random variations up and down that average value. So if you have, like a flat signal and you have some up and down variation around a flat value, that's the level component. Okay. Then we can have trend, which is systematic increase or decrease. It could go down, right? So if you see something like this that has a trend, then you could have seasonality, okay, where you can see that I took year 2 data. So where year 1 ends, year 2 data was going to go to the right of that, but I cut it and moved it back to plot them on the same months 1 to 12. And you can see that every year, the peak sales happen in summer around July, August, and then they happen a little bit more, there's a little bit of an uptick around December, and then, around April, May, there's a dip in sales and so on. So it's the same month-to-month pattern. Repeat, that's seasonality. Okay, so every summer you get the peak. Okay, every spring you get a dip. Every December you get a small mini peak. And so this pattern repeats year 1 to year 2 to year 3. And notice that, year 1, year 2 sales, their average levels are different. So there's a change in level from year to year. There could be a trend where the sales are trending down or trending up. But even while they're trending up and down, there's still that same month-to-month pattern where summer sales are higher than spring sales or something like that. So that's seasonality. Cyclical pattern, as I mentioned, is observed over many, many years. Unless you have a lot of data, like 20, 30 years of data, and you're doing long-term forecasting, you can ignore this. So you need to know conceptually what it is, but for practical purposes, there's basically a slow change in the level component over time. So you could see like a decreasing trend first and an increasing trend. As long as your trend is you're learning from the recent trend, soon after this you hit the bottom here, you'll pick up that the trend is positive now and you will adjust your trend. So you don't really have to explicitly model the cyclical component, but as long as your trend is flexible, it can change based on a few observations. Your trend will track it when the trend does change because of cyclical values over multiple years. Another cyclical pattern that sometimes we do incorporate is the product life cycle. So if we have different models, let's say for a cell phone, and we know a cell phone has a life cycle of about 3 to 4 years, nobody buys like a 3-year-old phone. So it's introduced, it goes up in sales, then kind of starts to fall down in sales. So that sort of cyclical pattern we can try to incorporate in our forecasting at the SKU level, especially when we know, okay, this SKU is 3 years old, it's kind of hitting end of life, and this new SKU is going to take off. So then you can incorporate that in SKU level sales, the product life cycle type of cyclical pattern. And then the unexplained component should have a mean of 0, because if it did not have a mean of 0, that mean would end up in the level and the trend components. So when you model the level and trend, the remaining unexplained variation is 0 mean, and it's just random variations around a 0 level, and that's going to be an unexplained part of the time series that we can't really focus. Kind of looks like random noise. Now let's look at an example. So what do we see? This is residential power demand in megawatt hours, and we have monthly data. So every 12 observations is 1 year. So we have over multiple years, it's monthly data. Okay, so what do we see? Do we see a trend? If you look at it, for the first year, the average is around 70,000. And then for the last year, the average is around 120,000 megawatt hours. So as the average is going up over the years, there is a trend, because the level for year 1 would be around 70,000. That's like the average around year 1. And the level for year 7, this is like about 7 or 8 years of data, is going to be around 120,000. And so this level is going up, that's trend. So there is trend. Now we can, level is always there. Level is, unless there's a 0 mean, you always have some level, like there's some level. So this level obviously is there, but there's trend. And then do we have seasonality? Yes, because if you look at it, around July, August is a peak, because this is May, June, July. The peak is kind of like in July. Every July, the demand for residential power goes is the highest. Right, and then January or February is kind of low. So in the winter, early in the year it's low, and then it kind of peaks in summer, right? Obviously, this is from an area which is like a warm area where a lot of electricity is used for air conditioning. Okay, so what we will say, given our options, that there's trend and seasonality. Horizontal means just level and seasonality. Level is also called horizontal. So C is not correct because the horizontal level or the level is growing over time. So there is a trend. So it'll be D, trend and seasonality. Now we have to be careful when there is a trend, especially if we have long-term data like this data, which is over like about 10, 11 years. What happened was at some point in 2004, there was a tax increase on tobacco products or smoking products. And we could see that before that tax increase, there was an upward trend. There was the consumption of tobacco products was growing, right? So if we had to forecast pre-2004, we would have a positive trend. We'll use that in our forecast. But when the tax was implemented, it became too expensive to consume tobacco. People switched to other things or just stopped smoking. And then you can see that the trend is negative. The consumption of tobacco started to decrease after the tax was put in place. And so if we have a rigid trend where we estimate the trend and the trend never changes for our data, we'd estimate almost like a zero trend for this data, but it's not zero trend. It's positive trend for the first half of the data and then negative trend after. It's like a trend changes. And so we'll look at, these Holt-Winters method where you estimate the trend based on recent observations and you allow the trend to change because some events could happen which could change the trend. So we'd use a method like that because if you have a long amount, several years of data, trends could change over multiple years and you can't just have a constant trend throughout your data. So this is important when you do have trend in your data, you have to ask yourself, for whatever amount of data I'm using, do I expect to have just one value of trend or could trends be changing over this time? Sometimes trend can be small, so data almost appear horizontal, but there could be a small level of trend. And sometimes certain events can change the trend, like as shown in this example. Now, sometimes our demand pattern is very difficult to forecast. Look something like this. Look at this demand pattern. So we have low sales, and then a couple of huge spikes, then low sales again, and then like maybe a small spike. So we get this spiky level. We have low sales to zero sales, and we get a huge spike, then low sales to zero sales, then a huge spike. There are specialized methods for such data, and really you have to figure out, instead of just trying to apply more complex statistical techniques, because they can only, some of them will try to predict when the next peak will occur, and then have a different model to predict the size of the peak. But these complex methods, they don't perform too well unless the spike is very periodic. It comes every so many weeks or months. It's a lot more fruitful to kind of ask what's causing this spike. Okay, in this case, for energy saving lights, manufacturers seized intermittent and very spiky demand because they were serving the downtown area of a city. Okay, and what was happening was like the life of the energy savings lights was like 10 years or 5 years or something like that. And every 5 years or every 10 years when the life ran out, the maintenance would be done and all the lights in the buildings would be changed. So this could be like 3 or 4 buildings designed to do maintenance, and it's been 8 years since installed the lights. So say all these lights are going to go bad over the next year or 2 years. And we don't want to have a person come in, change a light, go back, then call the maintenance crew again after a month, change another light. We just change all the lights of a building on one weekend. That's cheaper from a labor perspective than to keep changing lights as they go bad. So they place a huge order and these 5 buildings get new lights in that 1 month or that 1 year or whatever. And then a few years down the line, another few buildings, they hit their end of life and then they change all the energy bulbs lights. So this was the context where this data was generated. And if you have a context like that, you could give some discounts to companies to order the lights, let's say a few months ahead of time. So you have some reservations or some demand which is placed in advance. And then you don't have to carry so much inventory. When you get this advance order on which you give them some discount, you know, okay, that next year or next quarter, these buildings need new lights. So let me go and grab and have all those lights in stock, right? So you can do some sort of a reservation type of system for big orders. And for the small orders, you can just carry on as usual, have forecast the demand for small orders, kind of separate big and small order demand. So you have separate operations management for the big orders where the whole building gets lights changed, and then for residential customers who buy one light, two light here and there, you have a separate forecasting process, a separate inventory process to handle that demand, right? So that would be what you would do instead of just trying to throw a bunch of complex statistical methods at the problem, which is why understanding what's causing your demand can be really important. Okay, so now we're going to start our time series forecasting. And the logic behind these time series is going to be something like this. We can separate the time series into these three components: some average level, some trend, which is the change in the average level we expect from time period to time period, and some seasonality, which is going to make our values go up or down from some average level based on the month of the year or something like that. Now, all of these components of the time series have some noise in them, because the time series has noise. When you split up into these components, the components get some of the noise. So we're going to use averaging, some sort of averaging, to smooth out the noise, because the noise is kind of random. When you average it, it cancels out. So sometimes the noise has a positive influence, sometimes a negative influence, and when you average, these influences cancel out. So we're going to try to separate the components of the time series, smooth them, cancel out the noise, and then recombine them to build our forecast. Okay, that's our general logic for these time series methods we're going to do. So the very first method that's not really used other than to initialize some of these algorithms is called a naive forecast, which means that the sales in the next time period, my forecast for the sales in the next time period are my current sales. So if the boss tells me, hey, what do you think are going to be the sales in November? I look at the sales in October and say, hey, in October we sold this much, so November we'll sell the same amount. That's a naive forecast. Just move it forward, the current sales, and say that's the forecast. This is often not used as an end result. It's often used to initialize an algorithm or to use as a basis for judgment forecasting. So you start with a naive forecast and you adjust it up or down based on what you expect to happen next month. Okay. So now we finally get to the first mathematical time series method we're going to use, and that's called exponential smoothing. Okay. Simple exponential smoothing. So we're going to look at simple exponential smoothing. And this handles the situation where you just have some level, you don't have trend or seasonality. So just have some average level, and then there's noise and the sales hovers above. So with simple exponential smoothing, we are going to average out the noise and just try to discover that average level around which the sales hovers. Okay. Simple exponential smoothing will give more recent values more weight than the older values. So if you look at how we're going to weigh the 1 means the most recent value, 2 means the value like 2 time periods ago, 3 means the value 3 time periods ago. So the older the value, the less the weight it gets. Okay, and so it does consider old values too, but gives them very small weight, and most of the focus is driven by the recent values. So it's kind of like a method which is applicable when you feel that the recent values have more to say about the forecast than the very old values. And why would that be the case? If your trend is changing slightly, if your level is changing slightly, there's no trend like a systematic increase or decrease, but your average level of sales can go up and stay up for a few months, then might come down, stay down for a few months. So there's some variation in trend, in level, and then that's why you want to give more weight to the recent values to capture the recent value of the level, and less weight to the old values, and do some sort of averaging over them to average out the noise. Okay, so this method requires us to use a parameter called alpha, which has to have a value between 0 and 1. It should not be 0 and should not be 1, because 0 means we basically just don't update our forecast. So whatever the forecast was last time, we use that. 1 means that we basically do a naive forecast, just use the last month's demand as the future month's demand. So we don't want to do a naive forecast, and you don't want to never update our forecast. So it's always going to be value between 0 and 1, and not going to be 0 and not going to be 1. But theoretically, it could be 0 and 1. The math would work, but conceptually, we don't want it to be 0 and 1. We want it to be somewhere between 0 and 1. The bigger the alpha, the more the weight given to the recent values and the less the weight given to the old values. Okay, so this is the equation for our forecast. So the forecast F for the next time period t plus 1 equals alpha, the smoothing parameter, times the current demand dt plus 1 minus alpha times the forecast for the current time period, which I built in the past. Okay, so f of t is not the same as the current demand. So if I'm sitting in October, dt is the demand in October, the actual demand. Ft is my forecast for October that I made last month in September. That's my forecast for October using this same method. And I do a weighted average of the demand in October and the forecast in October using alpha and minus alpha as the weights to get my forecast for the next time period, which is November, Ft plus 1. Okay, another way to kind of understand this formula is to rearrange the terms using algebraic manipulation, and we get the forecast for the future time period equals the old forecast plus alpha times the forecasting error. Dt minus ft is the forecasting error. So think of alpha as a learning parameter. Dt minus ft is how much error you had. So if you had very small error in the last time period, we don't want to mess with our forecast too much. So we learn a little bit, alpha times a small value, and we adjust the forecast only a tiny bit. But if you had a huge error in the last time period, that means we're not doing a good job. So we try to adjust a lot more. So the huge error times alpha will give you a big value, and it'll change the forecast by a big value for the future. Okay. Both formulas are equivalent. They give you the same answer. It's just how to think about it. This is like a weighted average of demand, the recent demand and recent forecast. And this is like the recent forecast plus a learning parameter times the forecast error, dt minus ft. But they're the same thing. So as I mentioned, that alpha picks the weights. And if you have large values of alpha, you're giving more emphasis to recent values. And the forecast is more... it's going to change quickly, because what you're saying is things can change quickly. So all the change I'm seeing is not just noise. So I'm going to give recent values a large weight and react quickly to changes in the environment. A small alpha means that most of the changes you're seeing are noise and your situation is actually stable. So you want to do more averaging. Don't just look at the recent values, look at the old values too. Do a lot of averaging out the noise and have a more stable forecast which doesn't change much. So if you think you're in a stable business environment, use a small alpha. If you think you're a very dynamic business environment where things change a lot, only recent values are applicable for the next month's forecast, then use a larger value of alpha. Okay, so let's do this example. We have alpha is given in the question is 0.1. We have monthly data. We have the customers who the demand in terms of number of customers given to us for the first 4 months, and we have to forecast the demand for the 5th month. So time period t is 4 and t plus 1 is 5. We need ft plus 1 or f of 5, the forecast for time period 5, which we don't have. So how do we get that? So the forecast column would be blank initially. We'll just be given the month column and the customers column, like in a question on a homework or an exam. And the forecast column is what we are going to build out with our calculation. Okay, so we have to initialize the algorithm, because if you look at this equation, no matter where you start forecasting, you're going to need the forecast in the previous time period. So we have to start with not just a demand value, but a forecast value as well. So what we do is we say for month 2, my forecast is going to be the naive forecast. So how do you do the naive forecast? You take the actual value of the previous time period and say that's the forecast for this next time period. So 800 was the value in time period 1. Naive forecast says my forecast for time period 2 is just the 800. So I copy the 800 over here. Okay, and start off with a naive forecast. I say my F2, my forecast for time period 2 is 800. Now from F3, I can start using the exponential formula, because my formula for F3 is alpha times D2. D2 is 740 plus 1 minus alpha times F2, and F2 is 800. This is exactly this formula. Alpha times dt. So F3 will be alpha times D of 2 plus 1 minus alpha times F of 2, right? So this value right here, the 794, is F3. The way I get F3 is I say F3 equals alpha times D2, which is 740, plus 1 minus alpha times F2, which is 800. I calculate this and I get 794.0, which becomes F3. Now to get F4, I'm going to use D3 and F3. Alpha times D3 plus 1 minus alpha times F3, which is 794, and I get 795.6. And now when I have D4 is already given, when I have calculated F4, now I can finally calculate F5. So F5 is going to be alpha times D4, which is 790, plus 1 minus alpha times F4, which is 795.6, and I get my F5 of 795. So my forecast for the 5th month for number of customers is 795 customers. That's going to be my forecast. Okay, so let me show you how this looks in Excel. Okay, and this is my Excel sheet where I show you, and this should be made available to you through the learning management system like Canvas. This example is not the data in the slide you just saw, but again, is similar data where you have some values of Y and you have a time variable. This is what's given to you. Okay, what I want to show you here, first of all, is that in real life, the data you might get might come like this. This might be a date column or a year and month column. Year 1, month 1, year 1, month 2, year 1, month 3. Then you go to year 2, month 1, year 2, month 3. The month column goes 1 to 12, then resets back to 1. You don't want a column like the month column to be your time variable, because the time variable should change for every row. Every row should have its own value of time. You don't want year to also be a time variable. Year is not a good time variable. Why? Because it has the same value for multiple rows. All of these values of Y, I can't call this Y1, 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 Y1. They have to have a different time index. Okay, so year is again not a good time variable. Month is again not a good time variable, because after Y12, I'll go to Y1 again. No, that doesn't make sense. So I will just make a time variable and I put in an incrementing index of time. This is month 1, month 2, month 3. After month 12, I get month 13. Month 13 by definition means the second year, first month. Okay, and so on. And so you need a time variable that's always increasing. Time is always going forward. You don't want a time variable which wraps around. You don't want a time variable which stays at the same value for multiple observations. So if you have date values, you may have to split them or use them in some way to get a time column like this. Or you can just generate a time column by just incrementing the time and knowing that you have monthly data or you have daily data. You just know that between 2 and 1 is 1 month because I have monthly data. If you have daily data, between 2 and time 1 would be 1 day, right? So just generate a column for time like this. So these are the is the actual data, the time and the actual Y values. Now again, we want to start forecasting. And this is my simple exponential forecast in this column. So I can't forecast anything for the time period 1 because I don't know D0 and F0. Because if you want to forecast F1, the formula for F1 is alpha times Y0, or which was called D0 in the slide, plus 1 minus alpha times F0. But I don't have Y0 and F0. Y0 and F0. I don't have these values, right? They're the starting point. So I have to initialize. So I'm going to say I'm not going to forecast for the first time period. And for the second time period, I'm going to use a naive forecast. So I'm going to take the AD, which is Y1, and make it my F2. F2 equals Y1, naive forecast. And then from F3, I can start forecasting. So watch this. F3 is going to be alpha, which is given right here, times the 132, plus 1 minus alpha times the previous forecast of 80. Notice that for F3, I'm not using Y3 because I'm trying to forecast that. So never use the demand in the same row as the row for which you're trying to forecast, because F3 needs to be computed before you observe Y3. Okay, so when I compute this value of 106, I have not observed the 143. I only have, values for this data, the first 2 months. And I use this values to first calculate F1 and then F2, and I have not observed 143. Then once you observe Y3, then you can calculate F4. F4 is simply going to be alpha times Y3 plus 1 minus alpha times FT. So you have this Excel file, and you can look at it and look at the formulas and see how to build a simple exponential forecast. Once you do build a forecast, you can start calculating your error. Notice I don't calculate the error for time period 1 and 2. I can't calculate the error for time period 1 because I don't have a forecast for that time period. I can't have a forecast because there's no Y0. And then I can't do a forecast for time period 2 because I just use the naive forecast. So if I can calculate an error here technically, but if I calculate an error here, I would be calculating the error for a naive forecast, not for my method, which is simple exponential smoothing. The simple exponential smoothing kicks in at F3 at time period 3. So that's when I calculate the error. It's always going to be the true value. Y3 minus F3 will be the error here. Then Y4 minus F4 will be the error here. I can calculate the error, and I am taking the absolute value. That's why all error values are positive. Otherwise, sometimes the error will be positive, sometimes negative, right? For example, look here, our forecast is too high. So Y6 minus F6 will be a negative number, but it's showing positive because I took the absolute value. And then here I'm squaring the error. And then once you do all that, you can calculate the MAD. MAD is simply the average of the absolute errors. And you can also calculate the MSE, which is simply the average of the squared errors. And this one actually is the root mean square. So I'm going to take out the square root here. Okay, it's just going to be the average of the squared errors. That's going to be my MSE. Okay, some people like to do root mean squared error because the mean squared error looks kind of large because of the squared values. So then you can take the square root of the MSE. But if the question on the exam just asks you MSE, you would just do this one. Okay, this one. Okay, and now at Y time period 44, I can do a forecast, but I can also do a forecast at time period 45. Why? Because I have Y44 and F44. This forecast is simply a combination of alpha times Y44 plus 1 minus alpha times F44. Okay, so I get this value. But the limitation of simple exponential smoothing is it can only forecast one time period ahead. So I can't get a forecast for F46 until I observe this demand. So I'm just going to copy the forecast and keep it constant because I can't change it. There's no way to do simple exponential smoothing beyond this point because I need this data point that I will only observe when this time comes. And I'm currently sitting at this time, right? So your future forecast will just be the same. Now what I'm trying to show here is that I actually ran the forecasting over this time period, and then I saved some sales data for the 6 months, which is called a holdout sample. So I'm not going to use those values to figure out my value of alpha and kind of get my simple exponential forecasting right. I just use this values, and then say, okay, if I'm going to use alpha of 0.5 and use simple exponential smoothing on unseen data, this would be my 6 months of forecast. So my error will be a little bit higher if I do 6 months ahead forecasting, because right now these errors and these MAD and MSE values are for 1 month ahead forecasting. I'm always forecasting 1 month ahead. But if I was forced to forecast 6 months ahead, I'll just repeat the 1 month ahead forecast. But a lot can change in 6 months. and so I'll get a bigger error. This is useful to do if, let's say, you're not forecasting 1 month ahead, you need to get next year's forecast ready for some sort of planning, or next 6 months forecast ready. Then you might want to do something like this. Kind of look at, okay, if I do force my algorithm to give me 6 forecast values, in this case they're going to be the same, what the error might look like. So I kept a holdout sample to kind of calculate that. But this is not, at this stage, not that important. What you should understand is, how do we do the simple exponential smoothing? How do we calculate the absolute error, the squared error, and MAD and MSE? And you can look in the Excel sheet for formulas for that. Okay, so let's look at the chart. The Y values, the actual Y values are blue, and the exponential smoothing values are yellow. You can see that the actual sales data has a trend, is growing, and so simple exponential smoothing was not the right method to use here. And you can also see the yellow line, my attempt at using simple exponential smoothing on a data with trend, my yellow line is systematically lower than the blue line. I'm always behind because almost always my forecast is low. Okay, so there's a bias in my error. And you can also see it like this. If you don't take the absolute value of the error, okay, you just calculate the true value minus the forecast, and you take it down. You don't take the absolute value. Okay. Then your CFE would be the sum of these values without taking the absolute value, and it should be close to 0. But we'll get a big positive number because we have a bias. Our forecast is always lower, so errors are always positive. See, we got a huge positive number. There should be a number close to 0, like maybe 10, 25, minus 5, whatever. Should be close to 0. But we got a huge positive number showing that our forecast is biased. Simple exponential smoothing will be biased if there is a trend. Okay, it will be biased because it can't handle the trend. Okay, and so you can see that with CFE.